What if I told you that the reality you experience, this solid, predictable world of cause and effect, is just a shadow of a much deeper, stranger, and infinitely more powerful universe? And what if I told you that we, right now, have just built the key to unlock it? It's not a spaceship, it's not a telescope. It's a chip, a processor, forged in temperatures colder than the darkest void of space. But this isn't just any chip. This is a machine that doesn't just calculate, it explores. It dives into the very fabric of possibility. Today, we're not talking about a simple upgrade. We are talking about the dawn of a new age, a fundamental shift in what it means to compute, to solve, and to know. This is the story of Nighthawk, and it's the story of how our world is about to change forever. For decades, we have been living in a world defined by the relentless march of Moore's law. Computers getting faster, smaller, and more powerful every year. It's been an incredible ride, giving us everything from smartphones to the internet. But we are rapidly approaching a wall, a physical limit. The transistors on our classical chips are becoming so small. We're dealing with individual atoms, and at that scale, the weird rules of quantum mechanics start to take over. For most, that's a problem. For a visionary team at IBM, it was an invitation. They didn't try to fight quantum weirdness, they decided to harness it. And the result of that audacious gamble is here. It's called Nighthawk. This isn't just another step on the ladder of progress. Nighthawk, with its 120 quantum bits, or qubits, and the unprecedented ability to perform 5,000 consecutive operations, isn't a step. It's a leap across a chasm. It's the moment we stopped simply making our old tools better and started building an entirely new kind of tool. While some companies in this space are locked in a race for headlines, chasing a title called quantum supremacy, IBM has been quietly, methodically focused on something far more profound: quantum utility. They aren't just trying to prove a quantum computer can do something a classical computer can't. They're building a quantum computer that can do things we need it to do. They're building a tool to solve the unsolvable, to tackle the grand challenges in medicine, finance, and materials science that have stumped humanity for generations. Nighthawk is the declaration that the experimental era is ending, and the era of practical, world-changing quantum computing has begun. So, what makes this machine so revolutionary? To truly feel the seismic shift Nighthawk represents, we have to go back to basics and understand the fundamental magic at its core. Think about every computer you've ever used. From your laptop to your smartphone, they all speak the same language, the language of bits. A bit is like a light switch. It can be either on or off, 1 or 0. It's a beautifully simple, binary system that has powered our digital world for over half a century. But it's also fundamentally limited. A light switch can only be in one position at a time. Now imagine a different kind of switch, a quantum bit or a qubit. A qubit isn't a simple light switch, it's more like a spinning coin. While it's in the air, spinning, is it heads or tails? The answer is, it's in a state of both. It has the potential to be heads and the potential to be tails, all at the same time. This bizarre, mind-bending property is called superposition. A qubit can be a 0, a 1, or a delicate probabilistic blend of both simultaneously. This might sound like a small difference, but the consequences are astronomical. If you have 2 classical bits, you have 4 possible combinations. 0 c'est sûr, 0, 1, 10, 11. But you can only represent one of them at a time. With 2 qubits, thanks to superposition, you can explore all 4 of those possibilities at once. Now, let's scale that up to Nighthawk's 120 qubits. The number of states it can explore simultaneously is 120 times 2. It AC2 to the power of 120. That number is 1.3 nonillion. It's a 1 with 36 zeros after it. Let me give you some perspective on how impossibly vast that number is. The number of atoms in the entire observable universe, every star, every planet, every galaxy, every speck of dust, is estimated to be around 2 to the power of 80. Nighthawk ES computational space is literally, mathematically, larger than our physical universe. It is a machine that can hold more possibilities in its circuits than there are atoms in existence. This is why it's not just a faster computer. It's a new paradigm of reality simulation. Having a vast number of qubits is one thing, but making them work together in a meaningful way is the true challenge. Early quantum processors were like a group of brilliant geniuses forced to sit in a single file line. The person at the front could only talk to the person behind them, and so on. Information had to be passed down the chain, one by one. It was incredibly inefficient and slow. If you wanted to perform a complex calculation that required qubit Saturn 1 to interact with qubit Saturn 50, you'd have to perform dozens of intermediate swap operations just to get them talking. Each of those operations introduces a tiny bit of noise, a tiny chance for an error, risking the entire calculation. Nighthawk shatters this limitation with its revolutionary square lattice architecture. Imagine, instead of a single file line, our geniuses are now arranged in a grid, like a checkerboard. Each person can now talk directly to their neighbors, in front, behind, to the left, and to the right. The number of connections skyrockets. This high connectivity design is a game changer. It's like upgrading from a rural party line telephone system to a high-speed, interconnected social network. This isn't just an engineering tweak. It fundamentally changes the kinds of problems Nighthawk can solve. Complex algorithms often require intricate webs of interaction between qubits. On older architectures, running these algorithms was like trying to choreograph a complex ballet on a narrow tightrope. It was clumsy, slow, and prone to failure. The square lattice is like giving that ballet a grand, open stage. Qubits can interact more freely, more directly, and more efficiently. The number of operations needed for complex calculations plummets. This means we can build deeper, more powerful quantum circuits, the quantum equivalent of software programs, that were simply impossible before. This breakthrough in architecture isn't just about making things faster. It's about making the previously unimaginable possible. One of the biggest hurdles in the race to build a truly powerful quantum computer has been the scaling problem. As you try to cram more and more qubits onto a single chip, things get messy. It's like trying to manage a classroom. With 10 students, it's manageable. With 100 students in the same room, you get more crosstalk, more interference, more noise, and the whole system becomes unstable and less precise. For quantum computers, this noise is a killer, causing the delicate quantum states to collapse. IBM's answer to this is both elegant and brilliantly practical: a modular approach. Instead of trying to build one single, monolithic chip with 1,000 qubits, a feat of engineering that might be impossible with current technology, IBM designed Nighthawk to be a perfect, high-performance building block. Think of it like a super advanced Lego brick. Each 120-qubit Nighthawk module is a self-contained, stable, and powerful unit. The grand vision is to then connect these modules together. By 2027, the plan is to interconnect up to 9 of these Nighthawk modules. It's a system-level architectural solution to a physics problem. It's like building a supercomputer, not by making one impossibly large processor, but by networking hundreds of powerful, independent computers together. This allows IBM to scale up the quantum power exponentially while keeping each individual module within the realm of stable, controllable physics. It has a roadmap that takes us from the 120 qubits of today to over 1,000 qubits in the near future, without sacrificing the precision and stability that makes Nighthawk so special. This modular design is the pragmatic, engineering-driven path that could finally break the scaling barrier and lead us to the quantum systems we've only dreamed of. If the number of qubits is a quantum computer's width, its capacity to hold information, then its depth is how long it can process that information before it all falls apart. This is arguably the most critical and least hyped metric in quantum computing. The fragile state of superposition is constantly under assault from the outside world. Tiny vibrations, stray magnetic fields, even cosmic rays can cause a qubit to decohere, collapsing its quantum state back into a boring old 0 or 1, destroying the calculation. The number of operations, or quantum gates, you can perform before decoherence sets in is called the circuit depth. Think of it as the length of a quantum thought. If your computer can only perform a few dozen gates, it can only have very short, simple thoughts. It's not enough to solve anything meaningful. Nighthawk's ability to execute 5,000 quantum gates before decoherence is a monumental achievement. This is not just an incremental improvement. It's an order of magnitude leap in computational stamina. It transforms the machine from a short-term sprinter into a marathon runner. This depth is what allows it to run sophisticated algorithms, the kind that can actually tackle real-world problems. Let's put this in perspective. An algorithm that might require, say, 4,000 steps to find the optimal route for a global shipping company, or to simulate a complex chemical reaction, would simply fail on a machine with a lower gate depth. The calculation would fall apart before it could reach the answer. But with Nighthawk, that 4,000-step algorithm can run to completion. This is the difference between a tool that can theoretically solve a problem and a tool that can actually solve it. It's this stability and depth that allows Nighthawk to take on calculations that would occupy the world's most powerful classical supercomputers for years, and potentially deliver an answer in a matter of hours. That isn't just an increase in speed, it's a phase shift in computational efficiency. For years, quantum computing has been a realm of theory and promise. But with Nighthawk, the promise is becoming reality. We are now seeing the first tangible examples of quantum advantage, where these machines aren't just matching classical computers, but outperforming them in meaningful, commercially valuable ways. This is where the rubber meets the road. Take the world of high finance. It's a chaotic storm of interconnected variables, where predicting market movements is the ultimate prize. The global bank HSBC partnered with IBM to tackle a notoriously difficult problem: optimizing bond trading predictions. Using IBM's quantum processors, they were able to achieve a 34% improvement in prediction accuracy. Let that sink in. This isn't a lab result. This isn't a simulation. This is real data, a real business problem, and a real measurable result that could translate into billions of dollars. The quantum computer was able to see patterns and correlations within the data that were simply invisible to even the most sophisticated classical algorithms. Now consider pharmaceuticals and drug discovery. The current process is incredibly slow and expensive, largely a matter of brute force trial and error. Scientists have to synthesize and test thousands of molecules to find one that might work. Why? Because classical computers are terrible at simulating molecules accurately. Molecules are quantum systems, and to truly understand how a drug will interact with a protein in your body, you need a quantum computer. Nighthawk can simulate these molecular interactions with a level of precision that was previously impossible. It allows scientists to design a new drug molecule, atom by atom, on a computer and accurately predict its behavior before ever stepping into a lab. This could slash drug discovery timelines from a decade to a matter of months, leading to faster cures for diseases and personalized medicine tailored to your unique biology. This is quantum advantage in action. Not just doing things faster, but doing things we fundamentally couldn't do before. To make a qubit behave, you have to create an environment of almost perfect silence. You have to shield it from the noise of our classical world. That means getting it cold. Unimaginably cold. The processor at the heart of Nighthawk operates at around 15 millikelvin. To put that in perspective, absolute zero, the theoretical point at which all atomic motion ceases, is 0 Kelvin. The deep, empty vacuum of interstellar space, the cosmic microwave background left over from the Big Bang, has a temperature of about 2.7 Kelvin. Nighthawk's core is over 180 times colder than the coldest natural place in the universe. Achieving and maintaining this temperature is one of the greatest engineering feats of our time. It takes place inside a massive, multi-layered cryogenic refrigerator called a dilution refrigerator, which looks like a stunning, golden steampunk chandelier. Each descending layer gets progressively colder, using a complex system of pumps, pipes, and a mixture of helium isotopes to pull heat out of the system. But it's not just about the cold. IBM had to invent entirely new materials for the wiring and shielding. Materials that could conduct signals without conducting heat. They had to design intricate control systems that could send delicate microwave pulses to manipulate the qubits without heating up the processor by even a fraction of a degree. Building and operating Nighthawk is a monumental endeavor, on par with building the Large Hadron Collider or the James Webb Space Telescope. It is a testament to human ingenuity, a place where we have engineered a small pocket of the universe to be colder, quieter, and more controlled than nature itself, all to listen to the faint quantum whispers of reality. The greatest enemy of quantum computation is noise. A stray cosmic ray, a tiny fluctuation in a magnetic field, or even the act of measuring a nearby qubit can cause a catastrophic error, collapsing the entire quantum state. For quantum computers to become truly reliable tools, they need a way to protect themselves from these errors. They need a quantum immune system. Nighthawk integrates a groundbreaking approach to this problem with advanced real-time error correction. This is where the genius of the square lattice architecture truly shines. It's not just about enabling more connections for computation, it's also about creating redundancy for protection. Imagine the qubits in the lattice as a team of vigilant watchmen. A certain number of qubits, the data qubits, are performing the main calculation. Surrounding them are ancilla qubits, whose job is not to compute, but to monitor their neighbors. They are constantly checking the state of the data qubits, looking for tiny, telltale signs of an error. A slight phase shift, a change in energy. Here's the beautiful part. They do this without directly looking at the data qubits. A direct measurement would collapse the quantum state. Instead, they perform a gentle, indirect check, like feeling for a fever without waking the patient. If an ancilla qubit detects an error in its neighbor, the system's classical control hardware is instantly alerted. It knows what kind of error occurred and where, and it can send a precise microwave pulse to nudge the errant qubit back into its correct state, all in a fraction of a second. This entire process happens on the fly, without ever halting the main computation. This active error correction system dramatically enhances the reliability of the machine. It allows complex, long-running algorithms to succeed even in the inherently noisy environment of a quantum processor. It's the crucial step that moves quantum computers from being fragile, temperamental lab experiments to becoming robust, dependable computational engines. In the thrilling and often hyped-up world of quantum computing, you'll often hear the term quantum supremacy. This was a milestone claimed by Google a few years ago, where they demonstrated that a quantum processor could perform a very specific, carefully constructed task that would be effectively impossible for even the most powerful classical supercomputer. It was a stunning scientific achievement, a hello world moment for the quantum age. But IBM has deliberately chosen a different path. Their strategy isn't focused on supremacy, but on utility. The difference is profound. Supremacy is about finding a single niche problem, even an abstract one with no practical application, to prove a point. It's like building a drag racing car that can go 400 miles per hour for 6 seconds, but can't turn, can't carry groceries, and breaks down after every run. It's an amazing feat, but it's not a useful tool for everyday life. Quantum utility, on the other hand, is about building a machine that enterprises can actually use to solve their real-world problems. It's about building the reliable, powerful quantum truck, not the flashy drag racer. This philosophy permeates every aspect of Nighthawk's design. Its stable architecture, its focus on gate depth, its modular scalability, and its advanced error correction. These are the features you need not just to run one perfect experiment, but to run thousands of different experiments for hundreds of different clients, reliably and repeatedly. And crucially, IBM is making this power accessible. You don't need to build $1 billion lab with a golden chandelier to use Nighthawk. It's available to organizations around the world via the IBM Quantum Cloud. This democratic approach is accelerating global quantum adoption at an incredible pace. It allows researchers, data scientists, and engineers from any industry to get their hands on a real quantum computer, to experiment, to learn, and to start building the quantum applications of the future today. When a new technology is this fundamental, its economic impact is not just incremental, It's transformative. We're not just talking about a new product. We're talking about a new engine for the global economy. Analysts are already forecasting staggering numbers. They project that quantum computing could create over $850 billion in annual value by the year 2040. That's not a total market size. That's the new value created each year. And systems like Nighthawk, with their focus on practical utility and accessibility, are positioned to capture a significant portion of that emerging market. Where will this value come from? Think about the industries currently bottlenecked by computational limits. Logistics. Companies like UPS and FedEx could solve the traveling salesman problem on a global scale, optimizing shipping routes to save billions in fuel costs and drastically reduce carbon emissions. Materials science. We could design new materials at the atomic level, stronger and lighter alloys for aerospace, more efficient batteries for electric vehicles, or even room temperature superconductors that would revolutionize energy transmission. Artificial intelligence. Quantum machine learning algorithms could train more powerful AI models on exponentially larger datasets, leading to breakthroughs in natural language processing, computer vision, and autonomous systems. Finance. Beyond trading, quantum computers could perfect risk analysis models, pricing complex derivatives, and creating a more stable and efficient global financial system. What's more, IBM is building a powerful quantum ecosystem. By providing cloud access, they are fostering a community of developers, researchers, and businesses, all building on their platform. This creates a powerful network effect. The more people who use the system, the more tools and algorithms are developed, which in turn attracts more users, compounding the value for everyone involved. IBM isn't just selling a computer. They are cultivating the fertile ground from which a trillion-dollar transformation will grow. As incredible as Nighthawk is, it is still just a milestone on a much longer and more ambitious journey. It represents a class of machines known as noisy intermediate-scale quantum, NISQ computers. They are powerful, but still susceptible to errors. The ultimate holy grail of quantum computing is the creation of a fully fault-tolerant quantum system. What does that mean? A fault-tolerant quantum computer is one that can run any algorithm, of any length, for any amount of time, without a single error corrupting the final result. It would be the quantum equivalent of a perfectly reliable classical computer. It would require millions of physical qubits working in concert, with a large portion of them dedicated solely to performing real-time error correction on the others. This is the grand vision, and IBM has a clear roadmap to get there. The next major step on that path is a project codenamed Quantum Starling. Slated for 2029, Starling aims to be the first system to achieve full fault tolerance, capable of running a staggering 100 million quantum operations error-free. Reaching that milestone will be a watershed moment for humanity. It will mark the dawn of universal, stable quantum computation. At that point, the training wheels come off. We will have a tool capable of simulating reality with perfect fidelity, of solving optimization problems of staggering complexity, and of unlocking scientific and commercial breakthroughs that today we cannot even imagine. Nighthawk is the crucial, foundational step that makes that future not just a distant dream, but an achievable engineering goal. For so long, quantum computing has felt like it belongs in the realm of science fiction, a fantastical technology perpetually 20 years away. But Nighthawk changes that narrative. With its 120 powerful and well-connected qubits, its unprecedented 5,000 gate depth, and its proven ability to deliver a real-world quantum advantage, it firmly bridges the gap between abstract academic research and tangible, practical utility. IBM is proving that the path to quantum value isn't through flashy stunts, but through relentless, brilliant engineering. Through building systems that are not only powerful, but also stable, scalable, and accessible. Nighthawk is the engine, the cloud is the delivery system, and the global community of users is the fuel. The quantum revolution isn't a distant thunderclap on the horizon. It's the rain that has already begun to fall. It's happening now, quietly, in labs colder than space, running on chips that hold more possibilities than there are atoms in the universe. And Nighthawk is leading the charge. You know, as I've delved into this story, I can't help but see parallels to our own lives. The principles that make Nighthawk so powerful can be surprisingly profound guides for us. First, there's the idea of superposition. We often live our lives in a binary way. It's this job or that one, this city or another. But what if we embraced superposition? What if we allowed ourselves to hold multiple possibilities at once? To be both an artist and an analyst, to explore a side hustle while excelling at our main job. Living in that state of potential, before we collapse into a single choice, is where true creativity and discovery lie. Then there's the square lattice architecture, the power of connectivity. A single genius is limited, but a well-connected network of people can solve anything. Are you building strong connections in your own life? Are you reaching out not just to those in your direct line, but to people in different fields, with different perspectives? The quality of your network directly impacts the depth of the problems you can solve. And finally, IBM's strategy of utility over supremacy. In a world obsessed with appearances and winning, it's a powerful reminder to focus on what truly works, to build things of real, practical value, to focus on your own tangible progress rather than chasing someone else's definition of success. Build your skills, solve real problems for people, create genuine value. That is the path to lasting impact. The future is an incredibly exciting place, and the tools we are building are not just changing our technology, they are expanding our understanding of what's possible. I'm left with a few questions, and I'd love to hear your thoughts in the comments below. If you had access to a machine like Nighthawk, what is the one unsolvable problem, in science, art, or even your personal life, that you would want to solve first? And how do you think this technology will reshape our society in the next 20 years? Thank you so much for joining me on this incredible journey today. I hope you found it as mind-bending and inspiring as I did. Wishing you and your loved ones the very best of health and a future full of wonder. And if you enjoyed this deep dive and want to stay ahead of the curve on the technologies shaping our world, please consider hitting that subscribe button. We have so much more to explore together. Until next time,